Okay, so we are going to be using Google Colab to build a model using PyTorch. And so you're just going to go to Google Colab and you're going to create a new notebook. It should be on like the left side of your screen. And you're going to come up to like an empty page like this. And in Google Colab, there are kind of like two main things here. One main feature is that you can create text box to make your code sort of organized, to explain the code and all of that. And you can create code blocks for coding. First thing you want to do is import Torch. You want to import torch.nn as nn because this allows us to create the model, and we import matplotlib.pyplot as plot because that allows us to plot things. All right, to visualize. Now, the model that we're going to try to build is like a very, very simple one. So basically, look, let's just say I have a bunch of x values. All right, and x values, let's just say that's equal to torch.arange 1, let's just say 50 and 1. Now, what does this actually give me? Ooh, that's pretty cool. So actually I should do 51. Okay. Ooh, that's pretty cool. So it looks like it gives numbers from 1 to 51, or should I say 50? It actually doesn't include 51. The n portion right over here doesn't include this number, so it's the number it's kind of before it. And it looks like we're stepping, so each step that we take is 1. So this is our step size. If I made the step size 2, of course you would see that we're skipping by 2 every time. Right now our step size is 1. So given these x values, let's just create some y values out of this. Okay. Now, hopefully, y'all know the equation of a line by now. This is going to be y is equal to mx plus b. So given a whole bunch of x values, let's generate a whole bunch of y values with a slope and a specific y-intercept. Let's say that my slope is equal to 3 and my y-intercept is equal to 4. So therefore, my corresponding y values would just be equal to y is equal to my slope multiplied by my x values plus my y-intercept. That is the slope of the line. And if I print out my y values, and if I also print out the x values, you can see that the number 1 corresponds to number 7, number 2 corresponds to 10. You notice how this is like a linear relationship, right? So we're just generating a bunch of y values from a bunch of x values. All right. And the thing is that we're going to be training a model to try and predict the y values, but it's going to be starting from a random slope and a random y-intercept. So basically, if I just put a text box here, what we are trying to do is we have a model that is given a random slope and random y-intercept. And we want the model to fix that so that its slope and y-intercept looks like the values we have up top. All right. So we have a model, some sort of AI model, and it's going to be a random slope. So the AI model is going to have a random slope and a random y-intercept. So the outputs of the model is going to be very inaccurate. And what we want to do is based off that, inaccuracy, we want to make the model accurate by changing the y-intercept and its slope to look more like what we have here. All right. To make it look like the slope and the y-intercept that we have here. So let's actually build the model. So let's just say class model, and it's going to be an n module. In case y'all don't know what classes are, I'm just going to give a quick example. So let's just say we have class, and then let's say superhero. All right, I'm just going to create a random one. Now the superhero, this is going to have some properties, all right? And we initialize the properties, we init the properties. And for the init, we always pass in the self. And let's just say that the superhero has a name and has a power. Now, we can make the superhero's name equal to the name that we enter in. And we can also make the superhero's power equal to the power that we've entered in. So if we want to if we have a function here inside my class that says get the power, well, and then we always enter self here. If we want our superhero to maybe list out its power, we're just going to print self.power. All right. And also, if we want to, let's say we want to get the name of the superhero, once again, we enter self into this function. And this allows us to get the self.name that we initialized up here, right? So we're just going to print out self.name. So, for example, let's just say Superman is equal to an instance of my superhero. All right. Now, we have to enter in a name, which we're just going to say Superman. And we're going to give it a power. Let's just say strength. Okay. And let's put all of these in let's make all of these strings. So if I want to say superman.getPower, what is going to print out? Our power is going to be the strength that we put in here. If we want to get the name, superman.getName, well, we get Superman, which we put here. So classes, very, very good for, if you have a bunch of like objects that you want to create, and it basically organizes them. It's really easy to get, information about it. And yeah, classes are just really, really nice because you can have many, many functions inside here. So let's just create our model. First, well, as usual, we're going to find init, initialize some stuff, and we're actually going to run the super here, super.init here. Once again, another initialization thing. So now let's just say let's just say linear layer. All right, this is going to be our linear sort of line that we're going to create, sort of like what we have here. And what this is going to do is we're going to put this nn.linear, and then what we're going to do in this nn.linear is, well, we have a bunch of items here, right? So we can sort of treat all of these items here. So think about all the x values that we have. We can treat all of these x values right over here as sort of one item. So we're going to have an input of one item, right? This is going to be our input, and we're going to output one item that sort of looks like all these y values, right? So there's one input, which is this list of x values, and then there's going to be an output, which is one list of all of these y values. So it's going to take one input and one output. And then we have to define something called a forward function, because we have to sort of send our input into the linear layer. So what this forward function is going to do is it's going to take our input, and what we're going to do with the input is we're going to return self.linear layer, and then we're just going to put the input inside here. So we have the input, we put it inside this linear layer, and well, there we go. So now let's actually create an instance of our model. So let's just say my line model, let's just call it line model, is equal to an instance of my model. Okay. Now, if I look at line model.parameters, this is going to start making sense. All right. After I print this thing out, it's all going to start making sense. Actually, I have to do a list here. Oh, notice here, when we have this nn.linear inside my model, well, this nn.linear has a slope and also has a y-intercept. Ooh, that's pretty cool. So basically, we're going to start out with a random slope and a random y-intercept. And of course, that's going to lead me to random y values. But I'm going to change the model. The model is going to learn, and it's going to start making this slope and this y-intercept into this slope and this y-intercept that I have up here. Ooh, that's pretty cool. Now, how are we going to do this? We need a way to evaluate how trash our model is. And this is going to be the idea of a loss function. All right, a loss function. I'm just going to call it a loss func. Okay. Now imagine if this is our actual line, right? Our actual line is y is equal to 3x plus 4. Now my model's line right now is y is equal to, I don't know, it looks nasty. Let's just say it looks something like this. Pretty far off, right? Now, in order to find out how bad our model is doing, we could just measure the distance between the true value and my model value. You can see that the greater the distance between the two lines, the trashier my model is doing, right? So if we just measure the distance between the lines, let's say if I have 50 points here, 50 points here, just measure the points between these two lines, measure the distance between these different points, and I average them out, and I'm going to get a value, right? Of course, this is going to result in me getting a value telling me how trash my model is. Obviously, if the distance is greater, right? If the distance right over here is greater, then of course my value is going to increase, and therefore my model is going to be trasher, right? The model is going to be very bad at predicting. Meanwhile, if let's say my model was really, really accurate, and let's just say that it produces a line that looks something like this, which is very, very accurate. Well, notice how, just create the thing again. But notice how if my model creates a line that's very, very close to the actual line that I created at the start, notice how the distance between the two lines, or the 2 points, 3 points I shall say, that's very, very little. So the lower the value, you would say that the loss of my the loss, essentially the error. Think about like an error in the science experiment, right? The lower the value, the lower the loss that I have, and therefore the better my model is at its prediction for the line. Okay, so that is what we're going to be doing. And the loss function, this loss function that I was talking about, this is actually called L1 loss, by the way. So where you take the distance and all of that, the distance between the two points on the line, average them out. So let's actually set up the loss. My loss function, ooh, this is exciting. This is going to be nn.l1 loss. Ooh, nn.l1 loss, okay. We're also going to have an optimizer. Basically, a loss function isn't enough. Just because we tell the model that it's trash doesn't mean it's going to improve. We need some way that the model is going to improve. And that's where optimizers come in. Okay. Now, I'm actually going to pull up Desmos 3-dimensional graphing here. So, Desmos 3-dimensional graphing, and I'm going to share a graph with you guys after a little bit. But first, let's get into 3 dimensions. Okay. Now, this is, let's just say on the x-axis, this is going to be my model's slope. And let's just say on the y-axis, this is going to be my model's y-intercept. Now, every combination of slope and y-intercept is going to lead to some type of model evaluation. So we can say that on this z-axis, which would represent sort of the height of this function, let's just say that's our loss. So every sort of slope and y-intercept value is going to lead to a specific value for our loss. For example, if my line is super duper far off, well, let's just say my slope of a line, let's just say this is -2, and let's say my y-intercept is 500. Obviously, very, very far off from my actual line. So what are we going to get? We're going to get, so at this specific point, -2, 500, we're going to get a very, very high sort of, you can think about it as a very, very sort of high loss value, which is represented by the height. Okay. And this is actually a 3-dimensional function. Of course, right, you have 2 inputs, a slope and a y-intercept, and then the output of this is a loss value represented as height. And we can do more points, right? Let's say if my slope is 3, and let's say my y-intercept is, let's say, 4, well, this point corresponds to the actual line itself. So the loss value here would just be 0, right? And as I start moving further away from the actual value, further from the actual line, you can see that my loss essentially increases, right? As I move further away from this actual point, the loss is going to start increasing. Now, let's just say that if I graphed all of this out, let's just see. So this is, the x-axis would be my slope, and my y-axis would be my y-intercept. Let's just say that every combination of these points leads to a graph that looks like this, where, of course, our goal here is to try to get the loss to the lowest as possible. So we are essentially trying to minimize the loss, right? We're trying to go to this bottom of this cup-shaped thing, right? Because the lower our loss, the better our model is, right? The more accurate it is. And yeah, that's basically what machine learning is. It's basically, well, in this case, we have this model, and we're trying to minimize a certain loss value so that the model does the best. Now, how do we actually minimize the value? Well, imagine if we have a parabola like this. If the slope of my line here is positive, if I want to minimize it, I'm going to have to go to the negative direction of that slope. Meanwhile, if my slope is negative, as you can see here, well, then I have to go to the positive side, or to the right side, right? So if my slope is negative, then I go to the right, and if my slope is positive, then I go to the left. So it's sort of like the opposite of what you would expect, right? And this is basically the same case here, right? You can see that this slope right over here is, of course, positive, right? Because it's like a really steep sort of hill-like structure. Now, if I go to the negative direction of that slope, well, we're descending down this cup, and we are going to reach our minimum, okay? So that is what this optimizer basically does, all right? What the optimizer does is it basically changes the values. It changes the slope, and it changes the y-intercepts such that it's sort of going down this hill, right? It calculates the slope, and it goes to the negative direction of it such that it lands all the way at a minimum point. This process is actually called gradient descent, where you're basically minimizing the value of this function, okay? So let's just say my optimizer, that's going to be equal to torch.optim. And let's just say I'm going to use SGD. My parameters are going to be equal to my model.parameters. right? These are my model.parameters is basically the slope and the y-intercept that I'm trying to change. So I'm trying to change these values in my optimizer. So line model.parameters, and my learning rate is 0.01, let's just say. Learning rate basically tells you how fast are you going down this hill. Now, obviously, if I go down the hill too fast, I'm going to land up on the other side, right? So I don't want to go too fast, but I also don't want to go too slow such that it barely makes any progress. So choosing the right learning rate is also another problem in PyTorch, or just machine learning in general, right? You want to find a really good learning rate such that it's not too fast, that it skips the minimum, it's not too slow, that it's basically going to take forever to reach the minimum. So let's just run this and just wait for this thing to load. So now let's set up our training loop. Set up training loop. What the three hashtags do here is they kind of emphasize this. And if you go on table of contents, well, you can skip to that part, so it's very nice. And just a couple of other things. If you want to create like actual code comments, you can do, let's just say, print. Right? If I do this, it gives you like the actual like coding sort of comment thing. You can also have like sort of bullet points like hello, bullet points. So very good, cool stuff. There's also dashes, I'm pretty sure. Or sorry, the evaluation thingies, right? So you also have that. So yeah, pretty cool stuff you can do with comments. Anyways, let's just say I want to train my model 1,000 times. Basically giving it 1,000 times to learn from the data that I have for my x values, okay? So for every epoch in epochs, and range epochs, what I'm going to do is I'm going to set my line model to training mode so that it actually updates these values. Now my predictions, the line model is going to give some predictions out. So for example, if I do my line model, I enter in like a random value like 3, and we actually have to make this a torch.tensor so that it works. But if we put in the number 3 into my line model, sorry, both arguments, they are 0D and, I just have to put brackets around here. Ah, my God, float. Okay, you can see that when I put the number 3 into my line model, it's going to give an output of negative 1.58. So these are the predictions that my model sort of makes on the data. Obviously, this is very far off. When I plug in 3 into my y, or into my formula for the line, I get 13. So obviously that's way off. But when you just plug in numbers into my model, it's going to give an output, of course. All right. Now my predictions, we're going to use my line model. And what we're actually going to do first is we're going to put in my x values. And don't worry about this part, but basically right now we have to sort of change the dimensions of my x values such that it matches this one input here. Because right now, if I do ling x values, notice how it's 50 values, right? So it's like, but the thing is that my model only accepts one input. So what I'm essentially doing is I'm creating a list full of my x values so that now the length is 1, right? So that's basically it. So I'm able to plug in all of the x values in, and it's able to kind of look at all the x values as once. So my loss is going to be equal to, and in my loss function, I'm actually going to compare my predictions to the actual y values. And once again, we have to do the same process where we're adding a dimension and we convert it into a float. Then what we're going to do is we're going to do optimizer.zeroGrad. This basically does not track previous gradients. And what we're going to do next is loss.backwards. Loss.backward. And then optimizer.step. And whoa, what are these two things doing? Well, loss.backwards, that's literally just calculating the slope, essentially, right? So you can see that right over here, the slope is pretty high. And what optimizer.step is doing is saying, well, my slope is pretty steep, but I'm going to go in the negative direction of that slope so that I decrease my loss and I minimize the value for my loss in the long run. All right, so let's do this. And for every time we have a loss, let's just print out the loss. So we're going to say loss, and then this is going to be our loss. Let's see how our model is doing. Okay. So we train our model quite a bit of times. Let's train it some more. Let's see if it can learn more. Wait, 3, 2, 1, go. Let's see if our model is getting better and better. Hopefully we should see the loss going down. I don't know why it's going between 5.7 0.88. Oh no. It looks like what has happened is the reason why we were alternating between the two values there was our optimizer it kept on jumping everywhere. Maybe our learning rate was too high, but the model kept on jumping everywhere. That is not good. All right, instead of SGD, let's use an optimizer called Atom. So I didn't change anything. Still the same code. I just changed the optimizer, and wow, look at that loss. That is very, very low loss. This is very good, guys. All right, let's actually do something pretty cool. Let's print out my parameters for my model. All right, let's see how this is going. Oh wow, that is very, very accurate. Wow, it basically matched up. It basically matched up with what we had in the beginning, right? It saw that our slope and our y-intercept was very far off from its slope and y-intercept initially. So what it did was it basically calculated the distance between them, and it minimized the loss, or minimized the distance between the two. And wow, now the slope and the y-intercept values are fixed. That's kind of crazy. Wow. So let's just plot this. Let's visualize this. Visualize this. All right. So let's just do plot. Or let's actually do plot.figure first. And fig size is equal to, let's just say 12.6. What are we going to plot? So let's just plot or let's actually do a scatter plot. Maybe that's better. So let's just do x values and then y values. Show. And what this is going to do is going to create a scatter plot of my x values and my y values. So this is what it actually looks like, right? This is my actual values. And let's just create a label for this. Label is equal to actual values. And let's just make the color green, because why not? And to actually show the label, do plot.legend, which actually shows the label. So there is our label. Okay. And then we can also do plot.scatter x values, but instead of my y values, let's just do the predictions instead. And let's see how that looks like. So label is the predictions from model, and let's just keep it as its original color. So, can't call a numpy on a tensor. Sorry guys. I just had to kind of do something here. We had to convert this into a numpy array. Basically, there's like a torch array. So we have a torch array, and we also have like a numpy array. Technically, this is torch tensor, but let's just say this is a torch array, and this is a numpy array. The problem is that matplotlib, in order to plot this, it has to become a numpy array. So I just had to convert this to numpy. But yeah, you can see that my predictions from my model, that's pretty damn close. It basically looks exact, right? So yeah, this is how you build the model. And let's actually make the model do a prediction now. Prediction time. So for my line model, let's enter in the value 0. Let's see what we get. Torch.tensor. All right, it got the number 4, and guess what? When we plug in 0 in originally, think about it. If our x value is 0, 3 multiplied by 0 plus 4 gives me 4. Let's plug in the value 10. Or let's actually do a simple value, the value 50. We should expect to get 154. Let's actually do that. Ooh, so that is how we can evaluate this model. Thank you guys for watching.